I am Elena Lopez Aviles. I work at Coherent. I'm a senior optical engineer at Coherent. I'm in the East Granby side in Connecticut. Here in our side, we fabricate specialty optical fibers for different applications. And today I will be presenting stimulated Brillouin scattering, again in optical fibers. So let's explain a little bit what is stimulated Brillouin scattering. So this is a nonlinear process that happens in optical fibers, even at low input power levels. So let's look at what happens when the light propagates through a medium. So within the medium, the atoms and molecules are vibrating. These vibrations are referred to as acoustic phonons. These acoustic phonons scatter light in all directions. Part of this light is backscattered, and when this backscattered light interacts with the incident light, then as a result, it creates a change in the refractive index. And this periodic modulation of the refractive index is generated when the backscatter light and the incident light interact. This periodic modulation will reflect the light strongly. So this interaction, this interference is moving from left to right. From left to right. So it corresponds to a downshift in the frequency. In other words, scattered light is downshifted in frequency because of the Doppler shift associated with a grating moving at the acoustic velocity. What happened here? As we increase the power levels, the transmitted power will start to increase linearly, but at some point it will be saturated. Why this happened? Well, if we look at the backscatter power, beyond a certain point, the light will be strongly reflected. And the threshold pump power for SBS depends on the spectral width associated with the pump wave. It can be as long as 1 milliwatt for a CW pump or broad pulse of 1 microsecond width. So SBS in this case limits the power in optical communication systems. However, it can be useful in applications like sensors and fiber-based Brillouin lasers and amplifiers. So let's look at the physical process of SBS. So the process of SBS can be described classically as a nonlinear interaction among the pump and Stokes fields and an acoustic wave, which is initially generated thermally. The acoustic wave produces density modulations that in turn modulate the refractive index in the medium. This pump-induced index grating scatters the pump light through Bragg diffraction. This scattered light is downshifted in frequency because of the Doppler shift associated with a grating moving at the acoustic velocity, as I mentioned before. Both the energy and momentum must be conserved during each scattering event, where omega is the angular frequency of the acoustic wave and q is its wave vector. The frequency omega and the wave vector satisfy this phase matching condition given by this expression here, 4 pi over lambda, lambda of the pump and effective. So this expression must be satisfied. The frequency and the wave vector of the acoustic wave satisfy this dispersion relation for each acoustic mode M, where this Vm here is the acoustic velocity for each acoustic mode. In an optical fiber, the relevant directions are forward and backward directions. Stimulated Brillouin scattering occurs only in the backward direction, and this is because the angle between the pump and Stokes waves is maximum in the backward direction. So in other words, it's maximum when the angle is pi. This expression here is already taking into account that the angle is pi, and it's minimum when at the forward direction when the angle is 0. So even though SBS should occur only in the backward direction in optical fibers, spontaneous Brillouin scattering also can occur in the forward direction. And this happens because the guided nature of the acoustic waves leads to a relaxation of the wave vector selection rule. and as a result, a small amount of Stokes light is generated in the forward direction. This phenomenon is referred to as guided acoustic wave Brillouin scattering. In practice, the Stokes spectrum shows multiple lines with frequency shifts ranging from 10 to 1000 megahertz. However, this phenomenon, this spontaneous Brillouin scattering, is very weak. So the main one is a stimulated Brillouin scattering that happens in the backward direction. So to characterize the SBS gain, we use this expression, which describe the growth of the Stokes waves, and it's a form of Lorentzian. This is a Lorentzian form. This gamma B is the Brillouin line width, which is related to the lifetime of the acoustic mode, and is largely determined by the total acoustic mode loss. This AM here is the acousto-optic area. So this acousto-optic area takes into account the overlap integral between the optical mode and the acoustic mode. I will explain this later as I show you the console example. This omega m is a resonant frequency for each mode. This is, as I mentioned before, this is a resonant frequency for each acousto-optic coupling. This is this term here. This G0 is the peak value of the Brillouin gain at omega m equal to omega. This peak value of the Brillouin gain is mainly dependent on the bulk materials, on the properties of the bulk material. So all these parameters here are properties of the material. The relative strength, this relative strength here of each peak is a function of the mode property and is determined by this coefficient here. So this is property of material and this is property of the mode. I would like to mention here, all these expressions can be inserted into COMSOL as an equation. There is a box in the expression where we can insert these equations. So we did that in our model. I will show you an example here, how to calculate numerically the stimulated Brillouin gain spectrum. First, I would like to mention that we use 3 different COMSOL modules. Wave optics, of course, the base one, the multiphysics, wave optics, the acoustics, and we also use the labeling from MATLAB. Here, the MATLAB script, we create a MATLAB script, and it's used to set optical and acoustic parameters in the COMSOL model. So we can change these parameters directly to the COMSOL model using MATLAB. And also to sweep over a range of frequencies. And for each frequency, we calculated n number of acoustic modes. All this is within the MATLAB script. We just run the MATLAB script, communicates with COMSOL, and give us the results. So to define the parameters, we start our model defining the parameters. As I mentioned before, all these parameters here are mainly here from the material, and also some common parameters like the optical frequency, the optical wavelength that we working with. And here you see, here is where we inserted the Brillouin gain coefficient as an equation. So all this depends on the material that we are using. In this case, we were using silica for this example. So for the geometry, here we imported a custom refractive index profile and its corresponding acoustic velocity. Here I'm just for simplicity using a step index profile, but we can import any custom profile we have. Another way to do this is manually creating the profiles using the geometry and selecting a material within the COMSOL library material. Here we just manually imported it because in this case we can customize a refractive index profile and see what is the corresponding SBS gain, which is our goal here. So taking advantage of the symmetry, we use only 1/4 of the fiber to run our model. And we took, for simplicity, we took a constant value here for the material Brillouin line width with the using some of the literature values, we took 35 megahertz, which is a value that works for us when we compare our calculated results with experiment. So here is where we define, once we have our geometry, we have to assign a material. So the custom definition for the refractive index, this custom definition for these two are assigned into the materials. And here is where I have this expression. Here, this expression is for the optical, for the refractive index profile that we imported. And this is for the acoustic, which is the corresponding velocity, acoustic velocity for that refractive index profile. So we just assign it here in the materials. This is an important part. So in the pressure acoustic section, we define the damping of the acoustic modes. This damping of the acoustic modes is related to the Brillouin gain coefficient. So here we inserted this expression, which is which takes into account the acoustic velocity, and this material Brillouin line width is inserted here as a loss, because the acoustic modes have a line width, so they will decay. For the mesh definitions, we define two different meshes for the optical and acoustic mode. For the optical, we just have a regular coarse mesh, but for the acoustic, we need a finer mesh to solve for the modes, because the acoustic wavelength is smaller than the optical wavelength, so the acoustic modes have higher spatial frequencies. So that's why to obtain them accurately, we need a finer mesh for the acoustic modes. So let's start with the solution. Once we define our geometry, we inserted our equations, the materials, the meshes, we are ready to start solving. So we solve for the optical fundamental mode here. We did this one with this frequency, which is the velocity of the light over the wavelength, pump wavelength. And I'm searching in the modes around the refractive index of the core. Here I found it. I found my optical fundamental mode. This mode will be taken into account when we do the overlap integrals with the acoustic modes. So here is where we found the acoustic modes. In this case, we solve for several acoustic modes for each frequency. As I mentioned before, we sweep over a range of frequencies, and for each frequency, we find a number of acoustic modes. And for each of them, we need to do the overlap integrals to compare which acoustic mode will have the most interaction with our optical mode. So in this case, we search for acoustic modes around the phase matching condition. Once we have the acoustic modes, as I mentioned, the overlap integrals are calculated to obtain the acousto-optic area, which will be inserted into our Brillouin gain equation. The acoustic mode that overlap more with the fundamental mode will have the more contribution to the SBS gain. And as I mentioned before, we can insert the equations into our expression box to obtain other values. In this case, we obtain several values from our equation to make sure everything is correct. We use this global evaluation expression to run a table and see, okay, this mode has this overlap. This should contribute more to the SBS gain, and just to manually make sure that we are inserted the equations correct, that everything is going right, we use these expression boxes in console. And after we have all of our values, then the acoustic modes, the overlap integrals are calculated. We use MATLAB to sum all of the SBS gain for each mode to obtain the Brillouin gain spectrum. So as I mentioned earlier, with the labeling for MATLAB, we sweep We get the values, then we sum them, and that's how we get this SBS gain spectrum. This is the corresponding SBS gain spectrum for the step index profile that I showed you at the beginning. But this spectrum will change if we have a different refractive index profile. We have compared the several spectrum with literature and with experimental results, and we have very good agreement. Just for simplicity, and because I cannot share our custom profiles, I just use a step index profile to show you what we did, but the principle is the same. So to finalize this presentation, I would like to say what are the advantages and disadvantages of SBS. So depending on our application, SBS can be good or undesired. So in communications, we don't want it because it limits the amount of power that we can put in the fiber. But on the other hand, it's very good in sensing applications. That's because the velocity of the acoustic wave depends on the density of the medium. And this density changes when the fiber is under stress or when we change the temperature. So that makes a very good sensor. As a conclusion, with all the console models available, we have demonstrated a way to numerically calculate the SBS gain spectrum using a combination of the console models acoustic, wave optics, and live-link in our case. We can design optical fiber having SBS gain depending on the application. In fact, we have the capabilities in Coherent to design different optical fibers depending on the SBS gain level that we want. And with this, I would like to finalize my presentation.